I would like to describe some modeling problem about the nonlinear waves, strictly speaking nonlinear waves. And the word I used here in the title, the correct continuum limits and limits in plural, I will soon describe what do I mean saying this. And so the outline of my talk is that first I will say some words about the motivation of the studies, and then we proceed through the discrete weakly nonlinear model of the hexagonal lattice, but the main aim is the continuum model, and so the lattice model will be used only as a tool to obtain the continuum equation using the continuum limits. And here you can see that it turns out there are different possibilities to obtain the continuum equations, and that is why I used the word limits in plural in my title. And the technique to obtain the continuum equation in every case is a bit different. First of all, some words about motivation. Of course, it would be nice to describe an influence of an internal structure within the dynamic nonlinear statement of the problem. In particular, for crystals, it's possible to use the internal crystal structure to develop to obtain the model equations on the continuum level. And using the so-called correct continuum limit, so I will describe what I mean. And maybe this is an alternative approach to account for a microstructure, contrary to the pure continuum approach, when you add the gradient terms, for example, gradient terms in an expression of the energy. And finally, the choice of the hexagonal lattice is caused by the fact that this is rather simple, more or less simple, two-dimensional object, and also it's widely used in various modern problems like description of carbon nanotubes, graphene, and etc. Before proceed to the problem, I would like to call your attention on the fact that in the literature, two kinds of hexagonal structure are used. And this one, you see that the difference is in the absence of the central mass or particle in this model in contrast to that one. So for this model is often called by triagonal structure, but many others call it hexagonal as well. And so this model will be studied in the following, and it consists of we will consider how the central mass or particle interacts with 6 neighbors, and the interaction between the neighbors is modeled by the springs. So in the linear case, springs are linearly elastic, while in the nonlinear case, a more general model is applied. And so these notations I think they are obvious, because L is the distance between the masses in the model. Some words about the previous studies. Of course, the total number of the studies devoted to lattice is enormous, and I cannot note all of them, and here I call my attention on those which are most relevant to my study. And as for the linear works, I mentioned these papers because the linear problems for the model, for this model, has been performed there. This paper considers the so-called, what I called 1-2 field models that will be seen in the following, while that one considers just this kind of hexagonal structure on the linear level. As for the nonlinear problem, of course I would like to call your attention to this paper, because probably it was the earliest paper I saw where the different kind of continuum limits were applied for the usual one-dimensional monoatomic lattice. To say some more about an influence or the modeling of the microstructure, I would like to call these papers, and there more general models were developed where an interaction between the masses in the lattice were modeled by not only by means of the central springs, but also the additional degrees of freedom were incorporated, and finally this work also they deal with nonlinear description of this model. So let us begin. First of all, we would like to generalize the model of studied in this paper by means of the addition of the nonlinear part in the energy, where besides the usual linear disk interaction, elastic interaction between masses, weakly nonlinear part is added. So this is as a first step, because usually nonlinear problems are rather complicated for the analysis, and therefore employment of a more general model of interaction results in the equations which are difficult to analyze at all. And so we will consider the model of this, and certainly the variational principle allows us to obtain the governing equations, the discrete governing equations. However, certainly these are coupled nonlinear discrete equations, but nevertheless they are still rather complicated, and as a first step the following simplification is done. Let us only that all variations happens only in one direction, and therefore we can neglect the displacements in the perpendicular direction, and then instead of the coupled discrete equation, we obtain the only one discrete equation for the displacements of the mass in the lattice. Before proceed with the with the analysis of the nonlinear equation, it's useful to find out some results using the linearized version. So forget about this part for a moment, and let us try to find out the dispersion relation. And it seems that this dispersion relation has the following form. Here I remind you that it's necessary to use this scaling because of the discrete nature of the problem. And what is important in this relationship? May I remind you the more familiar problem about the one-dimensional monoatomic chain. And here the relationship is slightly is different. So it does not contain this part. And so what is the result of this part? If we draw the part of the dispersion curve, we see that the addition of the term in the dispersion relation gives rise to the additional extrema in the dispersion curve. So for monoatomic atomic lattice we have only one maxima, while for hexagonal lattice, for plane waves in the hexagonal lattice, we have additional maxima in the curve. And what this fact allows us to do? It's usual practice to consider the so-called long wavelength continuum limit. And usually for this purpose we consider the case of the small wave numbers, for the small wave numbers. Indeed, this is possible to do it in the framework of all models. And in this case, it's possible to check that if we consider this case, the ratio between the displacements of the neighboring particle masses, it tends to unity. We will see why this is important. However, it's of interest to see what happens near the other extrema. And first of all, if we consider this one, we see that we can apply the same kind of analysis if we assume that our wave number is not deviates slightly around 0, but around some constant value. And then instead of the real small wave numbers, we consider these small numbers. If we write down the displacements for the particle in this new notation, we can check that now the ratio between the neighboring particle tends to -1 as soon as k1 tends to 0. And finally, we can look at these points, and here we can see we can assume that the wave number may be expressed either this one or that one, and then for both cases we can obtain that now not neighboring but m plus 2 over xm tends to -1. How this it may help us for further analysis. So the general dispersion relation for small case for this case, it may be may be written in the form of the truncated power series expansion. And for the other cases, again, we can obtain the power series approximations, but of course for different case. And here we see that as soon as omega tends to 0, as k tends to 0, this is acoustical branch, while this one belongs to the optical branch because of this, and also the remaining estimations results in these two cases. So now let us proceed with the continuum limit. For this first case, this one, we see that because of this, the neighboring masses in the lattice, they lie on the same smooth curve, and therefore the continuum limit is implemented very simply, because as soon as the distance tends to 0, we obtain, instead of discrete system, we obtain the continuum system. And this is familiar technique, and then we can use the familiar technique of the continualization, and as a result, the governing continuum equation may be written in this form. Certainly this is not the exact representation. We neglect the higher order derivative term, but as usual, when we try to obtain the nonlinear equations which are suitable for an analysis, we would like to catch the so-called balance between nonlinearity and dispersion, because such a balance may help us to find out the possibility for a localized wave of permanent shape and velocity. And here there is this balance is between this nonlinear and dispersion term. This equation may be rewritten in the more familiar for the more familiar form using the transformation from the displacement to the strains, and then of course this is the famous Boussinesque equation, and this is integrable by means of the inverse scatter and transform method. It means that it's possible to find some non-stationary solution for this equation despite its nonlinear. However, an important information is possible to withdraw using a particular solution, and this particular solution is a traveling wave solution. So the direct integration of this equation allows us to obtain in particular this exact solution. And which important information is possible to obtain. So this part is this is an amplitude, and since C is the linear elastic model, it's always positive, while non-linear elastic model, which was incorporated in the model, it might be of either sign. It might be positive or negative. Therefore, the sign of the amplitude, which separates existence of tensile or compression wave, it's defined entirely by the sign of these nonlinear coefficients. So more general, by the properties of the material. And it's known that despite this particular solution, the rather arbitrary input evolves into the sequence of such waves, and therefore this prediction about the sign of the amplitude, it allows us to choose the suitable sign of the amplitude of the input that results in the obtaining of localized solution. And this fact has been confirmed in experiments, but not for lattice, for elastic rods and plates. So if you know in advance this result, you are able, and if you know the elastic moduli of the nonlinear elastic moduli, you are able to choose a suitable material where either compression or tensile localized wave may be generated. So certainly this one field model is familiar. This is not new. What is obtained for this hexagonal structure? It has been previously obtained the same results for the one-dimensional lattice, and probably it was one of the key works in the theory of nonlinear waves when the famous Fermi-Pasta-Ulam experiments were explained by means of this continuum limit. So the Zabusky and Kruskel, they obtained for the first time such a Boussinesq equation for this as a continuum limit in the framework of one field model for the one-dimensional chain. Now let us see what happens for the two-dimensional, for the so-called two-field model. It corresponds to this case, and here we see that the ratio of the displacements of neighboring masses tends to -1. So it means that the neighboring particles lie far from each other, and therefore they lie on different smooth curves, and therefore we cannot apply directly the same technique as we used for continualization in the framework of the one-field theory for the acoustical branch. We need to improve the technique, and what we have to do. The answer is seen on this picture. Since odd and even particles separately lies on the smooth, on each smooth curve, first of all we have to separate our lattice by odd and even particles, and separately we are able to perform the same technique as we did before. And how it is done? This is what was done by Zabusky and Dim in this paper. So we write down the equation, the discrete equations we obtain separately for odd and even particles, and introduce notations for different notations for displacements for odd and even particles. So instead of one equations, we have coupled equations, and now we, as I told you before, now we are able to do the same continualization as we did for the one-field model, and as a result, we obtain the following coupled nonlinear equations for this case. Here you see that besides certainly this is truncated. These are truncated equations because some negligibly small nonlinear terms are omitted. This we can call this negligibly small because we consider the weakly nonlinear case, and therefore as high is the order of nonlinear, the power of nonlinear terms, the lava it's in order, and the same is valid for the highest derivative of nonlinear terms. The lava it's in the order, and therefore we here we include in the model only the main nonlinear terms. However, it's a suitable change of variable may be employed in this case to write the governing equations in a more physically reasonable form. And these variables are as follows. You see that if U and V, so displacements of the odd and neighboring and even particle, they are close, like in the acoustical branch. This one will be 0, and we come back to the one field model, and if in the contrast, if they are of opposite sign, this variable is 0. So use the transformation of variable, we can obtain the following coupled equations for the variables responsible separately for acoustic and optical branches. And we see that these equations are linearly independent. So if we forget about nonlinear terms, they are linearly independent. Here we also forgot about higher order derivative terms. It's already it's also done because of this to achieve a more simple governing equations, when we are able to obtain at least some analytical results. And we see that in the framework of this model, the limit in case V equal to 0 exists, while U equal to 0 does not exist because of this term. It's impossible to, I don't know how to obtain the rather general exact solution of this system. However, traveling wave solution may be obtained. So introducing the phase variable, we are able to resolve these equations for U, for the strain, for macro strain, and substituting this relationship into the second equation, we obtain the ordinary differential equation, which is possible to solve because this is it corresponds to the modified KdV equations. And if we find the solution and look at the parameters of this solution, we always have to have these parameters to be real, and therefore it imposes the restrictions on the phase velocity c. And if we come back to the macro strain, we obtain the following relationship for it. And first of all, I would like to call your attention that usually when we find the solution for the nonlinear problem, the amplitude, the velocity, and the wave number, they are connected to each other, like here. However, for macro strain, due to coupling, there is no more dependence on the wave number and the phase velocity in the amplitude here, because of coupling. And so this is a rather exceptional case of the solution of nonlinear problem, where where amplitude is independent of the other parameters of the wave. And here we see the first difference from the case of the one-dimensional lattice, because this is rather important, because f equal to 0, not equal to 0 separates important cases of the localized waves on a pedestal or without it. And so we see that it's possible to check that reality of the parameters for the case of the one-dimensional monoatomic lattice is not realized, and therefore for f equal to 0 the solution does not exist, while for our case, for hexagonal structure, this is realized. And probably the reason is because in the discrete equations we have not only the neighboring the interaction between closest neighbors, but also with other neighbors. So this is the reason why of such a difference. And finally, how much do I have?
3 minutes.
Huh?
3 minutes.
So there is another solution for the model in the form of this. This is a Tench, which is described by Tench function, and the solution for macro strain is obtained in the same manner. And again, we see that the amplitude does not depend on the velocity. And when we consider the final case, which is realized only for the hexagonal structure, because there are no such extrema for the one-dimensional lattice. Here we have. I don't know how to draw it like I did it here, but if we look at this estimation, it's possible to see that now for the two-field model we obtain that the odd and even particle lie on two curves, while now they lie on the four curves. And so this results in introduction of four different variables that accounts for such a behavior. And then instead of two coupled equations that were studied in the previous model, now we have a system of four coupled equations. Again, we need in some more physically reasonable transformation of variables. The transformation of variables used for the two-field model is not applicable. However, it's possible to apply another one. I have found it in this paper. These papers, they use it for slightly different reasons, but it really works. And in particular, it's easy to see that when the limiting case is achieved, when U0, U1, U2, and U3 are equal to each other, then all these functions are zero and only acoustical branch remains. Then it's possible to see that other limiting case relating to two-fields theory, in particular to the two-field theory, is also realized as a limiting case here. So again, we are able to rewrite our model in the form of the four coupled nonlinear equations, and now it's even the use of traveling wave solution does not help us to find an exact solution. So here it's possible to use some kind of slaving principle using the fact that L is maybe small, and then the first equation, yes, it's resolved for the macro strain, but for the other equations may be resolved only approximately. And so if we do it, we can resolve U1 through the other variables and obtain the system of two coupled equations to be solved. And these equations are also possible to resolve approximately, and as a result the only one equations for arises, and now it's already possible to find the solution for it. And then coming back to the other variables, it's possible to reproduce the solution in an explicit form. But now we see that there is no independence of the amplitude on the velocity for the macro strain as was observed for the two-field theory. And to conclude, I would like to say that we see that different models give rise to different localized wave solutions, and the conditions for their existence, they are usually the intervals for this phase velocity when the parameters are real, and we introduced different variables for 2-field and 4-field theory, and besides the one who is responsible for macro strain, others others relate to the variations in the internal structure of the material, and we see that despite we reduce our original problem from the 2D to the 1D, there is a difference between the solutions in comparison with the 1D lattice model due to non-neighboring interactions arising for our plane wave description of the hexagonal structure. And certainly this is only the first step, and we need to see how the solution behaves when the second dimension is taken into account, like the transversion instability and the emerging of the solution which are described by the traveling wave solution. It should be checked in numerics how they emerge from the rather arbitrary input. Thank you for your attention.
I have been told, Francesco, that the restaurant will not serve us if we don't rush now to the place, so I think we must interrupt now and we will simply postpone. But there is one question here. Yeah. Okay, we have time for one question.
The question, when you want to change your variables from the four variables, you use the relevant variables that you use are related to the eigenmodes of the system.
System?
And the eigenmodes of the set as well, or not?
Yes, they have sense that because if you consider if you remind the results of the linear analysis, okay, and if you see that for example for the acoustical branch, the displacements of the neighboring particles are of the same sign, and therefore the first variable is responsible for it. The second variable is responsible for another maxima, and for.
So this remains even in the nonlinear case.
Yes.
Okay, thank you, Ray.
Меня просто это сделано.